Well, thank you all for taking the time to come. A pleasure to be here. I used to live in California, but I live now on the East Coast in Narragansett, Rhode Island. But I like the West Coast too, and I like Portland. I haven't been here in some years, though. My talk today is on software quality, a survey of the state of the art, based on lots of projects and lots of data. And I'm going to go through it pretty quickly, because even though we have 90 minutes, I have a lot of slides. Now, let me be sure. Okay. I started collecting this kind of data a long time ago. I have quite a few clients, big companies mostly I work with, some government groups, military groups, about 13,500 projects when I put the slides together, up to about 20,000 now. New data, 50 to 75 per month, 24 countries, and I also do expert witness work in lawsuits for poor quality, of which there are far too many. So I have some data from that too, which brings up a point. As some of you, we all know, last week, the government shut down, which is why a lot of people aren't here. Also, Obamacare went into production. And as you probably also know, the website didn't work. So people couldn't register for it. That's an example of why quality is important and why it isn't very good. The federal government, in one of their premier programs for the last 10 years, can't manage to get a working website up on the day the thing starts. That's an example of why quality needs to have a little more attention than it normally does. Now, some definitions of quality. Functional software quality means a combination of low defect rates and high levels of user satisfaction. Very important definition that I use a lot. Structural quality means a robust architecture so you can operate in a multi-tier environment without interfering with other applications. In other words, your software plays well with other applications. Aesthetic software quality is whether you like the appearance of something. Like a lot of us like the appearance of Apple stuff better than Microsoft stuff. That's a subjective issue, but it's nonetheless a significant one. Technical debt, introduced by Ward Cunningham. Powerful new metaphor, but unfortunately, not particularly effective as an economic metric. The idea of technical debt is if you make shortcuts and botch things up front, you have to pay for it later by fixing bugs and making repairs later. But here's what I pointed out to Ward. Projects that are canceled because their quality is so bad they never get released have a huge cost of quality but zero technical debt because nobody ever sees them. So you can't omit cancel projects. Another thing that's left out, I do a lot of work in lawsuits, as I mentioned. I've seen awards to the plaintiff for bugs in software that were 1,000 times more costly than the bug itself. And that's not a technical debt either. So if you leave out cancel projects and you leave out litigation, you find that technical debt only covers 17% of the true cost of quality. Good metaphor, gives you something to think about, but it's not by any means a fully formed economic metric. Cost of quality, overall cost of prevention, appraisal, internal failures, and so forth. Total cost of ownership, which I use a lot, is the sum of development plus enhancement plus maintenance from day one until the application is retired. Sometimes over 20 years, but I use a 5-year interval to calculate total cost of ownership for my clients. Now, I'm going to give you very quickly some quality hazards in 10 different industries, and then we'll get into the actual quality data. I'll start with airlines, which I just flew out here on. By the way, one of the problems of the closed federal government, the air traffic controllers are still up and working, fortunately, but the people that inspect the airplanes to be sure they're properly maintained, they've been laid off. So if you're sitting there in the plane ready to go home, which I'm going to be in a couple of days, you can be pretty sure they'll navigate you to the right place, but if the engine falls off before you depart, that part isn't covered at the moment because of the government shutdown. So in any case, these are the hazards in airlines. Air traffic control, by the way, remember some years ago, Los Angeles lost their air traffic control system. Over 500 flights had to be diverted. Not an uncommon problem. In any case, air traffic control, flight schedule confusion, navigation equipment, maintenance schedules thrown off, delays in opening airports, passengers booked in non-existent seats. I was on a plane once. It turned out that the airline had changed planes. And all of a sudden, there were a lot of people standing up, waving around, holding their boarding passes because people were sitting in their seats. When they changed planes, they brought in a smaller plane than the one originally scheduled, and they had like 50 seats missing in the smaller plane, but they didn't even slow them down from issuing the boarding passes. So all these people were getting on, and it delayed our takeoff for like an hour because they had to sort through and take some of the people off the plane. In any case, you get the situation. And then more recently, passengers misidentified as terror subjects. A recent example showed up in the paper. A baby of approximately 11 months old was identified as a terror suspect for having the same name as somebody else. Normally, although babies are annoying at that age, they're not really going to be serious problems. Okay, defense. Base security compromise, which we see all the time in Iraq and Afghanistan. Computer security compromise. By the way, there's a great new source of information on cybersecurity. It's published by the Congress. One of the few things that the Republicans and Democrats actually do together well. It's the Congressional Cybersecurity Report. I happen to live in the district of James Langevin of Rhode Island, who's the co-chairman of it. So if any of you want the URL of this Congressional Report on Cybersecurity, send me an email or ask me about it, because it's a terrific thing and it's free. In any case, weapons malfunction, like the Patriot missile that missed the incoming Scud in Iraq, was because of a software glitch. Command, communication, network problems, aircraft maintenance records thrown off, logistics and supply, satellites malfunction. Finance. Interest calculation error, account balances thrown off, credit card charges in error, fund transfers thrown off. By the way, speaking of fund transfers thrown off, I had a personal experience with that. I did some work in Italy, and they sent money automatically to my account, but then due to a mistake, they sent the payment twice to my account. Well, you can't just send them back a check because the second payment looks like taxable income to me. And so in order to correct what was basically a human error, but the software didn't allow that, it took 4 visits to a bank, involving one as high as the vice president, to get that actual mistaken money sent back to Italy without counting as taxable income on either side. So what a pain that was. Okay, mortgage, loan, interest payments in error, hacking, identity theft, and denial of service attacks, all big problems. Healthcare. Patient monitoring devices malfunction, operating room schedules thrown off, medical instruments malfunction, prescription refill problems, hazardous drug interactions, billing problems, and medical records stolen or released by accident. All common problems. And by the way, one issue with Obamacare, which neither Republicans or Democrats have paid much attention to, is going to be about a 30% increase in patients, but no increase whatsoever in doctors, nurses, or dentists, which means there's going to be a long delay in elective procedures. Some hospitals are going to shut down services. It's going to be troublesome as things unwind. Now, insurance. Policy due dates in error, policies canceled in error, benefits and interest calculations in errors, annuities miscalculated, errors in actuarial studies, payment records in error. All of these things happen. State and local governments, school taxes miscalculated, jury records thrown off, real estate transactions misfiled, divorce and marriage records misfiled, alimony, child support payments. I worked for a lawsuit as an expert witness for a case in California, actually, where it was a child support system. And one of the bugs in the software is that as the clerk updated the records, from time to time, the actual update would not be for the person whose name appeared on the screen in plain sight. It would be for some other person, which meant that the person who actually were paying their bills on time, some of those payments weren't getting credited, and they were having warrants set out for their arrests. Not because they didn't pay, but because of a bug in the software. Meanwhile, other people who may have never paid were getting these nice credits to their account for paying on time. So you see this kind of problem all the time. Traffic light synchronization throw off, and errors in property tax assessments. Do not take your town's value for your house at face value. You should probably challenge it almost every time because they're usually wrong. And by the way, they're wrong in a number of strange ways. Here in Rhode Island, where I live, the algorithms are owned by a company that the towns hire, but they're not revealed even to the tax collector. So if there's an error, you have no way of finding out the basis of the calculations. Manufacturing. Subcontract parts fail to arrive. Purchases, you order too much, just-in-time arrivals thrown off, assembly line shut down, aging errors for accounts receivable, accounts payable, pension payments miscalculated, other kinds of things happen in manufacturing. National government, tax records, annuities and entitlements, Social Security payments, all kinds of fraud occurs in the federal government with payments because there's no real awareness, no oversight on some of these things. Disbursements miscalculated, retirement benefits miscalculated, and then personal data stolen or released by accident. Public utilities, problems with electric meters, gas meters, distribution of electric power, billing records in error, nuclear power plants malfunction, and other kinds of things pop up too. And finally, telecom, switching disrupted, domestic calls disrupted, and billing records in error. So we have a lot of problems with quality in every industry. Bottom line is that software quality is blamed for more major business problems than any other, and poor quality has become one of the more expensive problems in history. That's because software does so many things and is used so widely, and it has so many problems. There are also many projects canceled that never get released. And as a general rule, the top executives of major companies, we're talking about the presidents, the board of directors, and the executive vice presidents, don't think much of their software community because we have too many canceled projects, too many bugs, and the quality isn't very good in a lot of the software when it's released. So that lowers our own chance of promotion in companies because the people who are likely to promote us, i.e. the presidents, don't think much of our competence. So we're less highly regarded than, say, electrical or mechanical engineers in some companies because we don't do as good a job, actually. In fact, I know some companies, automotive manufacturers, where a lot of the people who do embedded software refuse to be called software engineers because the status is too low. They want to be called an automotive engineer or mechanical, whatever their actual degree is, because they feel it raises the odds of getting promoted. Now, fundamental quality metrics. These are very important. And by the way, some metrics don't work, as I'll talk about in a minute. Defect potentials, originally developed in IBM in the 70s, but a powerful metric. That's the sum of errors found in requirements, design, code, documents, bad fixes. And a bad fix is a bug in an attempt to fix a bug. In about 7% of bug repairs, there's a bug in the fix itself. Test plan errors and test case errors. In some instances, there are more bugs in the test cases than are in the software being tested. And running buggy test cases doesn't do you very much. Defect discovery efficiency. That's the percentage of bugs you discover before you release the software. An important metric, but the next one is even more important. Defect removal efficiency. That's the percentage of defects you actually remove from software before you deliver to the first customer. The US average is 85%, now approaching getting a little bit better. The best-in-class organizations are over 99%. Every person in this room and every company represented in this room should know both your defect potentials and your defect removal efficiency. And I can tell you this, if you do not measure defect removal efficiency, you are below 85%, because nobody that doesn't measure DRE has a clue as to how to get up into the high 90s for defect removal efficiency, because testing alone isn't going to do it. What you need is a combination of pre-test inspections, static analysis, maybe some good defect prevention like quality function deployment, combined with testing done by certified test personnel using mathematically derived test cases. If you just let your developers test, a la some of the agile stuff, and they're not certified and not trained, and you don't do inspections and you don't do static analysis, your quality will always be mediocre and you'll have trouble getting above 90% of defect removal efficiency. And the good news is, if you get up into the high 90s in defect removal efficiency, you find to your pleasure that your schedules are shorter and your costs are lower than an 85 to 90% DRE. So the most important quality metrics in the industry are trying to measure defect removal efficiency and get into the high 90s because that benefits everything. It benefits user satisfaction, employee morale, executive satisfaction with what you're doing, shortens your schedules, lowers your maintenance costs. It generates enormous value, and it isn't even that hard a metric. It's perfectly easy to do. Let me give you an example. Suppose I'm building software, and I'm delivering it to you. What is your name, Kyle? I'm delivering it to Kyle in the first row. I and my developers find 900 bugs. We deliver the software to Kyle and his team. In the first 3 months, he finds 100 bugs. Well, after a 90-day interval, you take all the bugs I found and the bugs he found, you add it together. So the total now is 1,000 bugs. I found 900, he found 100, so my defect removal efficiency is 90%. Perfectly easy, straightforward calculations. You just keep track of the bugs you find, and then the bugs your clients turn in the first 90 days, and after 90 days, you calculate it. Of course, it's true there will be other bugs after, but that is still a good starting point, and that metric is very powerful. I regard it as the most powerful quality metric in the industry, because the companies that do that, especially those that are getting up into the 98, 99%, are the best companies, and they have the best QA organizations, and they have the happiest clients and the happiest customers. Now, standard cost of quality has been around for the 70s, and it's okay, but you have to modify it for software. I like to look at defect prevention like JAD and QFD, pre-test removal like inspection, static analysis, testing, and post-release defect removal. Now, another thing at the bottom. It was discovered in the 70s, but it's still true today, that bugs are not randomly distributed through all the modules of a big system. They clump in a small number of places called error-prone modules. Any of you use the IMS database product, an old product by IBM? We did an analysis of that. There were 425 modules. 300 of these were zero defect modules, never got a bug from a customer. 57% of the error density in that whole application were in 31 modules in one department under one manager. for whom other work was soon found. But it's a relatively common phenomenon to have error-prone modules, but your defect tracking system has to be sensitive to that, and you have to trace down the bugs and look at them by module, and then you have to sometimes do surgical extraction. You can't usually fix these modules in place because they're too buggy and too complicated. Now, quality measurement problems. If you're going to get good in quality, you have to know how to measure it. Unfortunately, the software industry does not measure quality well, and some of the metrics have been around for 50 years, but they're just plain wrong. Like, how many of you seen cost per defect? I must have read 500 papers saying costs 100 times as much to fix a bug here as it does there. That's a hoax. It does not. The problem with cost per defect metric is it penalizes quality and achieves its lowest value for the buggiest software. And it always happens that as you get rid of bugs, the cost per defect is going to go up because of fixed costs. Technical debt covers less than 30%. Lines of code ignores non-coding defects. Requirements and design defects outnumber coding defects. You can't measure those lines of code. So let me give you some samples of the problems with quality metrics. In this case, look at cost per defect. We have a high-quality application with 50 bugs. We have a low-quality application with 500 bugs. We write test cases, $10,000 each case. We run those test cases, $10,000 each case. We fix the fares, $10,000 in high quality, $70,000 in the low quality. So the total cost of removing defects, $30,000 for high quality, $90,000 for low quality. But look at our cost per defect. $600 a bug for the high quality, $180 a bug for the low quality. Now, what's wrong with that? Can you see the economic value of high quality? If your cost per defect gets cheaper the more bugs you put out? No, you can't do that. So you're going to understand the cost per defect is going to point you in the wrong direction and cause bad things to happen. So cost per defect is not going to work. Now, there's a basic law of manufacturing economics, which every other industry has understood for 200 years, except software. It seems to be a few years behind in economic topics. So what we have is this basic rule. If a manufacturing cycle has a high proportion of fixed costs, and there's a decline in the number of units produced, the cost per unit is going to go up. Everybody knows that, except us. Now, as quality improves, the number of bugs is going to get smaller. You're reducing the number of units. And so what's going to happen is that test preparation and test execution act like fixed costs. Therefore, cost per defect will go up as quality improves. So it's not a valid economic metric. It does not show the value of quality. And it throws off your top executives who don't understand these things and make you look dumb, because the better you get in quality, the worse you look if you measure cost per defect. Definitely not a satisfactory situation. Now, what about lines of code? Okay, here we have two languages. We've got Java and C. 50 bugs in Java, 125 bugs in C. They're both the same size, function points 1,000, but we have a lot more code in the Java example than we do in the C example. So if you look at defects per kloc, it's the same in both languages, 10 bugs per kloc. If we look at defects per function point, you can see the real economic value of a higher, better language, because it's only 0.5 bugs per function point in Java, 1.25. Look at the defect removal cost. Defect removal cost per kloc is the same in both languages, even though we spent 105,000 more fixing bugs in the C example than we did in Java. But if you look at defect removal cost per function point, you can see that high quality and better languages actually give you better benefits. And the reason that all of my data here is expressed in function points rather than lines of code and cost per defect is that I want to explain true economic value of quality, not some hokey number based on a number that goes backwards like cost per defect or goes off in strange directions like lines of code. So if you want to understand quality economics, you don't have many choices. Function points is the best choice for studying economic quality. Now, another basic law of manufacturing, it's the same one. If manufacturing cycle is a high proportion of fixed costs and there's a declined number of bugs, cost per unit is going to go up. If you select a line of code as a manufacturing unit, and you go from a low-level language like assembly to a high-level language like Ruby or Perl or Java or anything else, you reduce the number of units, but the cost of requirements and design, they're fixed costs. They don't get any smaller. So what happens is you've got a manufacturing cycle with a reduction in the number of units produced in the presence of fixed costs, so your cost per unit is going to go up. So your cost per line of code is going to go up for the higher level languages. So you can't use lines of code to measure the economic value of programming languages because they penalize the best languages and make basic assembly, or actually machine language, look like the best one, which is not really the way it is. So you got to know how to measure these things if you're going to get better at them. Now, these are US averages for software quality. And you note that in function points, unlike lines of code, you can measure requirements bugs. You can measure design bugs. So the total number of bugs on average is 5 bugs per function point. The defect removal efficiency before the software is released to clients is 85%, so you deliver 0.75 bugs per function point. But notice it's easier to get rid of coding bugs than it is to get bugs out of bugs and requirements and getting rid of bad fixes. So one of the advantages of this kind of measurement is it shows to where you concentrate your energy. And you plainly have to concentrate your energies on the bugs that are hardest to fix, like requirements bugs and like bad fixes. So testing, which only goes after coding defects, is one thing, but coding defects are easy to get rid of. You've got to get rid of requirements and design defects, and you can't do that with testing. You need inspections and some other things up front before testing begins. Now, best in class. Anybody here actually measure this kind of stuff in your company? Well, since this is supposed to be the cream of the crop of the Pacific area of quality, you all should be doing this. Everybody in the room should be doing this. And you should all be getting numbers at least as good as this. 2.5 bugs per function point, 96% removal efficiency, delivering only 0.13. This should be the minimum entry requirement to come to this conference. I wouldn't let you in the door. In fact, if you didn't have this kind of data in your company, because you shouldn't be here. You should be in some other kind of work, like farming, more appropriate than trying to pretend you're in quality if you don't know this kind of stuff. Now, this is what happens when companies really botch it up. 8 bugs per function point, 62% defect removal efficiency, over 3 bugs per function point delivered. These are the things that show up in all the lawsuits that I work on, which are unfortunately far too plentiful. Now, since I have thousands of data points from hundreds of companies, here's the things that always work. These give you more than 90% success with a lot of different companies and a lot of different projects. You want to use formal inspections, you want to use tech static analysis, as well as code static analysis. You want joint application design, you want requirements modeling, you want to use functional quality metrics like function points, you want to measure cyclomatic complexity, you want to measure defect detection and defect removal efficiency, use automated defect tracking tools. You need a big quality assurance group of over 3% of your total software population. You need mathematical test case design, usually based on something like design of experiments. You need quality estimation tools. You need certified testing specialists, and you need root cause analysis. Everybody in this room should be using all of these things, but I'll bet you're not. Okay? These are the things that have mixed quality results. You get about a 50% success rate. CMMI level 3 is good, but the best CMMI level 1 groups are just as good as the worst CMMI level 3 groups. And there's a bunch of companies like Apple that don't use CMMI at all, and they're as good as CMMI 5 in some cases. So it's a nice indicator, but it's not the only indicator, and it's not a sufficient cause. ISO and IEEE quality standards, so-so. Six Sigma methods, if they're tailored for software, they can be good. Quality function deployment, it's hard to do, but it does work well if you do it right. Independent verification validation, only done for military projects and not very efficient, 10 or 15% efficiency. Quality circles, they work in Japan, not over here. Clean room methods, not so good. Kaizen is moving from Japan to the US and is looking good. Cost of quality without software modifications, marginal, and pair programming. Pair programming is very expensive, marginally efficient. Has about a 15% reduction in defects at about twice the effort that goes into the project. So it's not a very good economic solution. It's much cheaper to use static analysis and inspection than it is to do pair programming. Furthermore, pair programming doesn't really deal with requirements and design bugs on big systems. So it's only a partial and costly solution. Now these are the things that don't work at all, or at least they don't work very much, 25%. Testing is the only form of defect removal. If you don't do inspections, you don't do static analysis before testing, your quality is never going to be very good. That's the end of the story. Like it or leave it. And if you don't believe it, measure your defects and your defect removal efficiency and find out for yourself. And the fact that nobody here measures that, you don't know your own quality. But I can tell you from the hundreds of companies that I've worked with, if you do only testing with no inspection and no static analysis, you will not have very good quality. That's just the way the method works. Passive quality assurance, total token quality assurance. I was invited out to a company in Cleveland by the vice president of quality. And I came. I was anxious to see what they did because it's a big, important company. And when I got there to the vice president, I said, when are you going to introduce me to your staff? And he said, we don't have a staff. I'm the only one. So they had a vice president of quality, but no quality assurance organization. It was just somebody that they could introduce to clients to say, see, we have somebody in quality. But they didn't really do anything about it. Lines of code, which remits non-code defects, cost per defect, which penalizes quality. Failure to estimate quality risk early. You should be able to know how many bugs you're going to have before the project starts, because there's plenty of historical data about it, and everybody should do that. And then quality measurement leaks. There's a lot of gaps and omissions in quality metrics. For example, very few companies even start measuring until testing, which means you have not a clue on your requirements and design bugs. IBM and the good companies start measuring during design inspection, requirements inspection. They keep a continuous stream of data statistics from the first day of requirements all the way through as long as the software is in use, and everybody else in this room should do the same thing. Now, this is what I regard as a good definition for quality. A low defect potential, less than 2.5 bugs per function point, high defect removal efficiency, more than 95%, requirements that don't change by more than about 2.5%, explicit requirements achieved 97.5%, high user satisfaction ratings of 90% on installation, ease of learning, ease of use, functionality, compatibility, error handling, user information screens, customer support, and defect repairs. So you've got to be good in all of these things. But the two top ones, low defect potentials of below 2.5 per function point, high defect removal efficiency are the two most important. And you'll find if you do that, that customer satisfaction is directly proportional to release defects. You give customers a lot of bugs, they don't like the rest of your software. You give them a few bugs, they like it. So you've got to get low defect potentials and high defect removal efficiency to be good in these other things too. Now, here's some observations based on a lot of projects. Individual programmers are less than 50% efficient in finding bugs in their own software. Normal testing, often less than 75% efficient in finding bugs. If you only do unit test, function test, regression test, system test, and acceptance tests, do not expect to be above 80% in defect removal efficiency. Do not expect happy clients either. Do not expect fast promotions because your CEO knows that you're a jerk. So if that's the way you're going to do things, you live with a penalty. Design reviews and inspections average more than 65% of top 90%. Static analysis also the same, although 55% is probably closer today. And inspection, static analysis, and testing combined can give you lower costs and schedules by 25% and lower total cost of ownership by 45%. So if you put together a synergistic package of defect prevention, pre-test removal, and formal testing by certified experts, you can get very good, very cheaply. You can be much better than you are today and lower your costs at the same time. Now, if you're going to get rid of bugs, prevent them, you've got to know where they come from. So this is where bugs come from. Requirements are the hardest to prevent and repair. Requirements creep, which averages between 1% and 2% per calendar month, are very hard to deal with, very troublesome and a source of bugs. Architecture is a key to structural quality. Design bugs has the most severe and pervasive kind of bugs. Coding bugs are the most numerous but the easiest to fix. Security flaws are hard to find and hard to fix. Documentation bugs in the user manuals and the help text can be serious if you ignore it. Bad fixes. These are secondary bugs in an attempt to fix it. I worked in a lawsuit once on a financial application, and the original bug in the financial application caused my client to have to restate their prior year's earnings, which is embarrassing for a company to do that, and it lost them a very valuable banking relationship. So they sued the vendor. The vendor tried to fix the bug 4 times. Each of the first 4 fixes failed, and each had new bugs that weren't there before. Finally, after 9 months, the 5th fix fixed it, but by then it was too late, which is why they were sued. So there were errors in every attempt to fix this major bug, and it took them 5 attempts to do it. Bad test cases, numerous but seldom measured. I'll bet most of you in this room, if you have a test library, have as many bugs in your test library as you do in the source code that you tested. But probably, unless you work for a company like IBM, you don't know that. Because only leading, or maybe some of the other, anybody here with a company like a Motorola or a Raytheon, the high-tech companies know this kind of stuff. Banks and insurance companies usually don't have a clue. So if you work for one of the high-tech companies, you probably have a chance of knowing this kind of stuff. Data errors, web content, and structure. And all of these things need to be studied and need to be improved. Now, something happened to the alignment here. Probably because this is a Mac and this was originally done on a PC and we're just reading it from a thumb drive. Okay, this is the number of defects per function point for data defects, coding defects, test case defects, website defects, design defects, requirements defects, all the way down. The total is 12 defects per function point. But you quickly see one of the advantages of function points, as opposed to lines of code, is that you can't measure requirements and design and data defects with lines of code, but you can measure all these things with function points. So it's the most general purpose metric. Some of you are agile folks and you use story points. Well, that only works for agile applications. You can't compare story points to, say, a project using RUP or a project using TSP because they don't use stories. So function points can work for agile, but story points don't work for anything but agile, so it's useless for comparison between agile and anything else. In any case, 12 bugs per function point. Now, if you look at high severity defects, severities 1 and severity 2, these are the defects that actually cause the software to stop completely or to misbehave seriously. Things like major errors in financial applications. Design defects are 17% of the total. Coding defects, 15%. Structural defects, 13%. Data defects, 11%. Requirements creep, requirements defects, website defects, security, and so forth. It adds up to 100%. But you can see that you've got to go after the most severe sources first, but you want to go after design, structural, and data defects and requirements creep, as well as coding defects, because collectively they're a bigger number than coding defects. So you've got to go after everything, not just coding defects. When you look at low severity defects, 3s and 4s, minor little errors, coding defects are on top, followed by data defects. As an example of a data defect, one that's annoying to me, my name is Capers Jones, C-A-P-E-R-S. I get bills from companies calling me Casper, C-A-S-P-E-R. That's not my name, and I don't like it either. And it's not really a software problem. Some live person keyed in the wrong name, but it's almost impossible to get it fixed. So normally I have to live with it when it happens, because getting that fixed in a large company like an American Express or something is almost impossible. But it's troublesome. In any case, this is the distribution of defect sources for low severity defects, with coding being on top, followed by data defects. Now, duplicate defects. And if you've got thousands of customers, someone are going to find the same bug and report it to you. In fact, the record, the largest number I saw, was over 10,000 reports of the same bug on the same day in a WordPerfect release that stopped the software from being installed. So naturally, everybody reported it because they couldn't install the package. It shut down the phone system in the state of Utah because so many calls were coming in on this particular bug. I also worked with another company. I shared an office space with them. It was a security company. They had a very sophisticated security thing based on calendars, but they left out a leap year. So on February 29th, every one of their clients, starting in Japan, when the sun came up, they were all locked out of their systems with no easy way to get in. So their phones started ringing because every company was locked out. But in any case, this is the origins of duplicate defects. Coding defects, structural defects, data defects, security, requirements defects, design defects, bad fixes, requirements creep, test cases, total defects. So these are the sources of duplicate defects that we have to deal with. Now, invalid defects. From time to time, you get bugs that are not really your fault, but they're submitted to you anyway. I noticed that Michael Ma is here from QSM. Okay, some years ago, when I was running another company, Software Productivity Research, a client of QSM sent a bug report to us. Well, I knew Larry Putnam, we were friends, so I routed the bug to Larry. It wasn't a very severe bug, but it was sent by accident to the wrong company. And I'm sure QSM got bugs that were really assigned to us, sent to them too. I just mention it because even though it wasn't our bug, it took like an hour and a half. You had to send a response back to the user saying, we have received your bug and we're routing it to the correct location. Then you had to send the bug to the right company so they could fix it. And that took administrative time. It didn't take any technical time. None of the programmers looked at it. I mean, once we found out it was for the wrong product, nobody had to do anything to it. But it still took like 90 minutes of administrative costs to get a bug sent to the right place when it was sent into the wrong company in the first place. So in any case, for invalid defects, data defects, structural defects, website defects, user errors are big in this kind of stuff. Document defect, another user error that was intriguing. This you probably have seen before. This is back in the days in 5 1/4 floppy disk. Somebody called in complaining our software didn't work, and after 10 minutes of discussion discovered they'd put the disk in upside down. It worked fine when it was inverted. In any case, requirements creep, requirements defects, code defects, and architecture defects at the end. So, turns out that fixing security bugs is the hardest and most costly kind of bug repairs that you have to deal with, followed by design defects, followed by requirements creep defects, followed by requirements, structural defects, architecture, data, bad fix. You'll notice that out of the 14 sources of defects, coding is way down there at number 12. So the basic point is that there's a lot of other kinds of bugs that have to be measured and studied and dealt with more than just coding bugs. And one of the weaknesses of the software quality community is an excessive concentration on coding bugs and almost a total oblivion to the other more expensive, more serious kinds of bugs that also need to be dealt with, especially security, design, requirements creep, and so forth. So these are the other issues that you have to deal with. Now, this is what it would cost a Fortune 500 company to recover from various kinds of problems when they occur. Security defects, about $200 million. Design defects, $175 million. We're assuming a large portfolio of 5,000 applications, 10 million function points. This is not a small company. This is a big company like a General Motors or an IBM, somebody in that size category. Anyway, a lot of money goes into recovering from various kinds of defects in the course of a year. Security, design, requirements, data, code, structural defects, requirements creep, website defects, architecture, and so forth. That's one of the reasons the CEOs don't think much of us, because they spend a lot of money fixing bugs in the stuff that we deliver and install. No doubt, whoever put the government website up for Obamacare is getting a lot of heat today, and has been ever since it was first discovered that it didn't work, and justifiably so. It turns out, and this surprised me when I first discovered it, Severity 2 bugs, by the way, Severity 1 means the software stops cold, it doesn't work at all. Severity 2 is a major feature is disabled. Severity 3, a minor feature is disabled. And Severity 4, it's a cosmetic error. It surprised me when I first discovered it that Severity 2 bugs are harder to fix than Severity 1 bugs. Normally a Severity 1 bug, when the software doesn't work at all, it's fairly concise, it's 1 or 2 lines of code, and you find them and fix them and it goes away. Severity 2 defects, where some major feature is disabled, are often subtle defects that are widely spread through multiple modules and multiple ports of the application, and they're really difficult to track down. Down below, see the one that says abeyant defects? That's a category that originated in IBM, and what it means is a bug that occurs for one customer and one customer only. You can't make the bug occur on your software, in your computer, nobody else can either. It's some special combination of software and hardware at one customer site that causes the bug to occur. And sometimes you have to send live people out there to find out exactly what caused it, because it's such an obscure bug that you can't do it any other way. So abeyant defects, which are not plentiful, not numerous, are extremely troublesome when they do occur. Now, defect repairs by application size. Little applications, 10 function points, are pretty easy to fix. And this shows size from 10, 100, 1,000 to 100,000, up to 100,000 function points. By the way, how many of you in this room use function points? Not a big show of hands, in fact, not any. So let me give you a couple of starting points. How many of you use Java? All right, 53 Java statements is equal to 1 function point. How many of you use C? About 128 C statements is equal to 1 function point. I can give you this kind of information, although I don't have it in my head, for about 200 programming languages. And you can get from commercial sources relationships between source code statements and function points for around, actually for a total of almost 1,000 programming languages. So if you don't know function points, at least you know enough from the data that I give you for Java and C. And if you use COBOL or Fortran, that's about 105 statements per function point. If you use SQL, that's around, I think it was 25 statements per function point. Anyway, I can't remember it all in my head, but there's that kind of numbers available. In any case, but as you can see, that big systems are harder to fix and take more time than small applications. This is not a surprise. It takes more effort, for example, no doubt, to fix the roof of a skyscraper that's 100 stories tall than it is to fix a chicken shed, because it's just harder to fix these big structures. So this shows the effort and the cost by size. Now, this shows interesting information that not many people know about, and I want to give you a little explanation of what it is. The left axis shows the number of users of the application. The horizontal axis shows the size and function points. Look at the combination where you have 1,000 users and 1,000 function points. What that's telling you is that 27% of the bugs delivered in the software to those 1,000 users will be found and reported in the first year. There's a strong correlation between finding bugs and number of users, and another correlation between the size of the application and number of bugs. If you have 10 million users down here at the bottom, then they'll report 90% of the bugs in the first year. If you only have one user, you're only going to get 12% of the bugs in the first year. So the number of bugs reported to a software company is proportional to the number of bugs that are there, of course, but also to the number of users. And that's one of the reasons why you have some very interesting deviations in bug reports for the same software. It's really based on how many users are using it to show how many bugs are going to come in the first year. Now, this is elapsed time for defect resolution, how long it takes to actually find and fix bugs, and then the total days involved. If you look at the static analysis, the leftmost column, 1 day to get ready to run it, 1 day to execute it, 1 day to repair, 1 day to validate the repair, 1 day to integrate, 1 day to distribute the repair back to clients. 6 elapsed days. If you look over at the system test, 8 days for preparation, 6 days for execution, 2 days to repair, 4 days to validate, 4 days to integrate, 3 days to distribute, 27 days. The point of all this is that actually finding and fixing bugs is not where all the costs go. There are other things that have to be measured to know the true cost of quality. Specifically, how long it takes to get set to do testing, how long it takes to write the test cases, how long to run them, how long it takes to integrate the repair back into the application, how long it takes to distribute it. There's a whole bunch of cost elements. So software quality is much more complicated than just finding and fixing bugs. So you need to understand, for economic purposes, all of these things, and also for calculating defect turnaround time. Now, this is the distribution of software by severity level. Severity 1, total failure is only 1%. Severity 2, statistically it's 20%, but it really isn't. The reason for that is that companies fix high severity bugs faster than low severity bugs, and clients want bugs fixed in a hurry. Well, you can't fake a severity 1 bug. You can't claim that the software doesn't work at all, but it's easy to fake a severity 2. By some bug that you want fixed in a hurry, you call it a severity 2 bug and give it to the vendor so they'll fix it in a hurry. So the actual true value of severity 2 bugs is probably around 7 to 8%, but statistically it shows up as 20% because low severity bugs get forced into that category. And then you also have structural multi-tier defects, invalid defects about 15%, duplicate defects about 30%, and abandoned defects less than 5%. So this shows the distribution of defect reports. Now, this is an important slide. I've used this slide for many, many years. If you are going to have poor quality, you don't do static analysis, you don't do requirements modeling, you don't do inspections, your early costs up until you start testing are going to be comparatively cheap. If you do inspections, if you do run static analysis, your upfront costs during requirements and design are going to be a little bit expensive, or at least more so than the other case. But towards the middle of coding, when you get set to do testing, the lines cross. And the high quality line, where you did requirements analysis, inspection, static analysis, all that kind of stuff, that line stays almost flat forever. The poor quality line, all those early savings, because you skimped on stuff, in other words, you were mounting up a huge volume of technical debt, that line goes up like a hockey stick, and it's never going to come back down again. So you have a momentary savings during requirements and design compared with a huge technical debt that lasts forever. So economically, it makes sense to get it right before you get into testing. The main reason that projects run late, the number one reason that projects run late, is that the testing interval stretches out to 2 or 3, maybe 5 times longer than planned because there are too many bugs when testing starts. If you don't have any bugs when testing starts because you did static analysis and inspections, testing zips right through. I have a friend of mine when I worked at IBM who was actually testing the IMS product. He was at work for a solid week. They were testing 24 hours a day, and he was there second, third shift a lot of the time. When he finally got home, he found a note on the fireplace that his wife had left him. And I don't blame her. Would you want to stay around being married to somebody who never came home because they were testing something around the clock? When we went and installed inspections and better quality control on IMS, testing dropped from 90 days of 3-shift testing to 30 days of 1-shift testing. So that shows you the economic value putting in inspection and doing things right before testing begins. Because the main source of grief, schedule delays and everything else in the software industry, is that testing takes too long, and it takes too long because there's too many bugs. So get rid of bugs before testing starts by doing it right up front with inspection, and everything compresses, and that's why you have shorter schedules and lower costs with high quality than you do with poor quality. Now, this shows a number of different industries. System software are things like operating systems and telephone switching systems. These control large and complex physical devices. The defect potential is 6 per function point, removal efficiency 94%, delivered defects 0.36, first year discovery rate 65%, first year reported defects 23%. Look over there at the military side. Very complex stuff. These are weapon systems like the Patriot missile, the cruise missiles, things of that sort. 7 bugs per function point, 96% removal efficiency 0.28, first year discovery rate of 75%. Now, why do you find military bugs so quickly? Well, if you fire off a cruise missile and it lands on the bow of your ship, you know you've got a navigation bug you want to fix before you send off another one. So military bugs, you fix them in a hurry because otherwise the things blow up in your face. So you got to get them right. Banks and insurance companies, not so much. That's why the first year discovery rate of things like information system is only 30%, because not too many bad things happen, and so the bugs are not found immediately. Information systems, 4.5 bugs per function point, 73% efficiency. Commercial software like Microsoft, 5 bugs and 90% efficiency. Outsourced software, 5.2, 92% efficiency. So you can see these differences by category. Web software, only 4 bugs per function point, 72% efficiency, but a first year discovery rate of 95%. That's because a lot of web applications have millions of users. And as I already showed, when you have millions of users, you find bugs quickly. Embedded software, like I have hearing aids. That's an example of embedded software. My wife has cochlear implants, an even better example. 95% removal efficiency, but also good first year discovery rate. SEI CMM3, SEI CMM1, you see how the variations are. And then you can see the overall national averages based on all of those things. But the point of all this is that those averages are misleading. You got to know which industry you're working in and which size projects to have really good handles on how many bugs you're going to have and how you get rid of them. Software size and defect removal efficiency. Very few bugs in small projects, very high defect removal efficiency. As you can see, as the applications get bigger, the defect potentials goes up and the defect removal efficiency comes down and the number of delivered defects goes up proportionally. That's why you still have bugs after years in Microsoft Windows, where there's still bugs in Windows 7, Windows 8. It's because it's over 100,000 function points, so it had a lot of bugs in it. And even though they have pretty good testing and pretty good pre-test removal techniques, there's still a lot of delivered defects in it. How many of you use the CMMI level, Software Engineering Institute Capability Maturity Model? Well, only a couple of hands. In any case, the higher levels like 5 and 3 have some potential advantages for lower defect potentials and higher defect removal efficiency. These are for big systems. The previous one was for 1,000 function points. This is for 10,000 function points. It's the same story, but for the bigger systems, you have more bugs and lower efficiency than you do for the small. Now, this shows various software methods. I'm sorry the lines aren't there. Waterfall, 5.5 bugs per function point, 80% removal efficiency, 1.110. Agile with Scrum, 4 bugs per function point, 90% removal efficiency. PSP and TSP, 3.5, 96%. Model-based and 85% certified reuse. I see Carl Wiegers is going to be giving a talk here on reusable materials. Very advantageous if you can get 85% certified reusable materials across requirements, design, code, and other deliverables. Very low defect potentials, very high numbers of defect removal efficiency. This is the same story for 10,000 function points. Waterfall, iterative, object-oriented, agile with Scrum, RUP, PSP and TSP, model-based, and 85% certified reuse. You can see all the ranges and variations. Clearly, agile is much better than waterfall, but not really any better than PSP or rational. In fact, if you're doing, anybody here doing software that needs either FAA or FDA certification, agile's not a good choice for that. It's too loosey-goosey. You need more rigor. So RUP or TSP would be a better choice for medical devices or military avionics packages that need various kinds of certification. Or for that matter, civilian avionics packages like a Boeing, for the navigation packages. Now, this is some data that shows countries. Japan and India are both very good in quality. Japan is #1, India is #2. Scandinavia is pretty good. South Korea is good. Canada is good. Switzerland, United Kingdom, and Israel. These are all countries that have pretty good defect removal efficiency and relatively low levels of defect potentials. Here we are in the United States. We're okay, but we're in the middle of the pack. Not as good as Japan and India, but better than France and Germany. So you can see how these things vary from country to country. And what you really want to know is in your specific company and the projects that you do, what is your defect potential and what is your defect removal efficiency? And if your defect potential is below 3 per function point and your removal efficiency is more than 95%, go tell your president, because that's good news. That's something that they would like to know, and they probably should know. So everybody should measure those two values, and then if your numbers are favorable, when you start getting up above 95%, you've got all kinds of things that you can use to improve your own status internally, and your company can use to look better than your competitors. Because if your competitors don't know, and you do, then you're obviously doing a better job than they are. Now, this is a very simple, easy chart that anybody can use and anybody can deal with. What this shows is defect potentials on the left axis, defect removal efficiency on the right axis. And presumably most of you, well, from the things that I saw from the hands raised here, you're all somewhere between malpractice and the US average. There's nobody down in the best-in-class category. At least if you are, you didn't raise your hands. So you're somewhere there between US averages and malpractice. And what you want to do is to plot your projects on this kind of chart, and you can plot all your projects in your company and see how you're doing. Now, this shows what happens when you start plotting projects by size. 100,000 function points are moving up towards the malpractice zone because they have a lot of bugs in them. Then 10,000, then 1,000, then 100, then 10 function points. Now, if you people in the room are dealing with small projects of a couple hundred function points, you might be towards the best-in-class thing because they don't have many bugs in the first place. So if you're dealing mostly with small applications, you're in a good position because they don't have as many bugs as the big ones. But if anybody in this room is dealing with 10,000 to 100,000 function points, given the show of hands that you raised, I'm surprised your company's still in business. Because none of you in the room, based on the hands, know enough to successfully build 100,000 function point projects. You don't do inspections, you don't do static analysis, you don't measure anything, you don't keep good quality data, and all you do is test. You can't do 100,000 function points like that and hope that it's going to work. You got to kind of step up and do it right. Now, this shows various methodologies, and you can plot the methodologies that you use on the same table. Cowboy, not good. Waterfall, not good. Low-level capability maturity models, not good. US average. Pair programming, a little better than average. Extreme programming, looking pretty good. CMMI5, Integra Nova, which is a Spanish company. TVEC, TSP, and RUP are all down there in the best-in-class categories. So what you want to do in your company is obviously move down towards the best-in-class category, but you got to know where you are on this chart before you know where to move to. So you got to first know where you are today, and then lay strategies in place to get down to the best-in-class end of the spectrum. Now, this is a little hard to explain, but I'll tell you what it is. Oh, no, not that hard. The next one's hard to explain. This shows how various kinds of things stack up in terms of this chart. Manual proofs of correctness, pitifully inadequate. Testing only by the developers who are not certified test personnel and who do informal testing, not very good. Test by certified testers, test and static analysis, tests, inspections, and static analysis, combined with automatic defect proofs and requirements models, that gets you right down there into the best-in-class category. But testing only by developers, you're going to be average at best, and maybe even not average. You could even be worse than that. And also you need defect removal efficiency measures, and you need mathematical test case design. So the bottom line is if you correlate the kinds of quality control methods you do, then you can guide your path down there towards the best-in-class into the spectrum and get away from the malpractice and average into the spectrum, which is what you all want to do. This shows, this is the one I said was complicated. These are the kinds of applications that either are worse or better than US averages. Bungled outsource contracts, the kinds I do expert witness on, they are way up there in terms of malpractice. Program stock trade software, you know, the stuff that every now and then shuts down the Dow Jones or causes some 500-point decline in stock values because of some huge glitch in a stock trading software. That's another thing that damages the US economy. Local taxes, property tax assessments, all of those assessment programs are buggy and they cause wrong values. Here, I live in Rhode Island. In a duplex, two identical houses in the same structure, the property tax on the one on the right was twice as high as the property tax on the one on the left. They were, you know, in the same structure almost. In other kinds of things where you have row houses, you can have property tax variations of 25 or 30% for houses of the same square foot built by the same company on the same lot looking the same direction. That's not right, that's a bug in the software, but because the algorithms are proprietary and you can't get access to them, it's very difficult to get those things fixed. Okay, where are we now? Billing and retail ERP packages. I worked as an expert witness in an interesting lawsuit. It was a lawsuit against an ERP vendor by its own shareholders who claimed that the quality was so bad in the ERP package it was lowering the value of the stock. And a further claim was that the quality was so bad the company couldn't use its own product inside to keep its own financial records. That case settled out of court, but the fact that it was filed in the first place is a sample that big systems, an ERP package is around 250,000 function points. They're about as big as it gets. But these things are not easy to build. Okay? Anyway, open source is surprisingly good. Anybody here do open source? You use static analysis? See, open source, for various reasons, is better than a lot of internal companies. They tend to do a lot of things right. So I'm pretty impressed with the open source quality model. Finance, large outsourced vendors like IBM and some of the others, they tend to know what they're doing, computer aid. And then down here on the left, the things that get better move towards best in class. Systems embedded, telecom, medical, avionics, and weapon system. Let me tell you why they're in the best in class category. If you are building, for example, a complex medical device like a CAT scan device or an MRI, that can hurt patients, kill patients if you don't get it right. So there's huge liabilities, and because of huge liabilities, there's also a huge need to do quality. So they have very sophisticated quality control in medical devices. Same kind of thing with embedded software, like the brakes on an automobile. You've seen all the damages and things that happen when those systems fail. So anybody that has software with a large legal liability, or even worse, the potential of criminal charges if somebody's killed because of a bug in the software, they have every reason to be sophisticated in quality control, and most of them are because they know the consequences if they don't get it right. So the commercial systems, embedded, telecom, medical, avionics, and weapon systems are usually the ones that are approaching the best-in-class status because they have huge liability issues and they have to be there. Now, here's a simple example of measuring defect removal efficiency. What I'm showing here, example 1, is inspections plus static analysis plus testing. We found 390 bugs from inspections, 350 from static analysis, 250 from testing. Subtotal, you found 990 bugs. The clients found 10 bugs in the first 3 months. So a total of 1,000 bugs were found. You found 990 of them, so 99% defect removal efficiency. Good number, good example. Everybody should try to get to this level. Now, let's look at the next case. Okay, this case we used inspections, but we didn't do static analysis. So what happened? All the bugs that we found by static analysis in the first case weren't found here. So now we found 960 bugs, delivered 40. So we're 96% defect removal efficiency. Well, let's take a look at the third case. This time we didn't do inspection, but we did static analysis. So now we deliver 75 bugs. We found 925 and delivered 75. So our efficiency is only 92.5%. Now look at case 4. This time we didn't do either inspections or static analysis. All we did is testing, which basically is 90% of the audience of this talk. So this is only 85% defect removal efficiency. This is why companies that don't measure this kind of stuff aren't very good in quality, because they basically don't know enough to be good in quality. So you've got to put in this pre-test stuff, inspections and static analysis, if you want to get into the good numbers of defect removal efficiency. Now, industry-wide defect causes. Requirements, design, security flaws, interface problems, logic and branching and structural problems, memory allocation, testing omissions and poor coverage, test case errors, stress and performance problems, and bad fixes and regressions. This is the universe of bugs, of bug causes that we need to try to improve and make better, starting with requirements, design, security, and so forth. We need to concentrate on methods of reducing the defect potentials in all of these categories. Now, if you go above 95% in defect removal efficiency, this is what you'll find as benefits. Your schedules will be shorter, your productivity will be higher, you'll have high levels of user and team satisfaction, you'll have low levels of delivered defects, you'll have very low levels of maintenance costs, and you'll have low levels of a risk of litigation. So you benefit almost everything you can benefit with software at the same time, and it isn't even very expensive to do. In fact, doing inspection and static analysis is cheaper than what you're doing today. Only you don't know that because you don't measure. So if you start measuring and if you start doing things right, you can shorten your schedules, lower your costs, and be a much happier group than probably your teams are today. Now, if you're going to get rid of bugs and eliminate them, you need to know where they come from. This shows the defect statistics from a lot of different organizations. SPR is my old company. IBM found 45% of customer-reported bugs came from design. My old company found 20% came from requirements, TRW 60% from design, MITRE 64%, Nippon Electric. Bottom line is at the front of the cycle, the front of the development process has more bugs than coding. So that means that your quality control approaches has to include things like inspections and joint application design and quality function deployment that concentrate on front-end bugs because they're more numerous and more severe than coding bugs. And if all you do is coding bugs, that isn't adequate. You've got to get the upfront ones. Now, what you need is a synergistic combination of defect prevention and defect removal. Defect prevention are things that lower the number of bugs you're going to encounter in the first place. And they include, although there's more than this, structured design and joint application design, structured code, use of inspections. Inspections, by the way, have a double hit. Not only are they 85% efficient in finding bugs, but people that participate in inspections spontaneously avoid making the bugs that they see from participating. So you get a downward yield of bugs by people who use inspections up front. You prevent bugs as well as finding them, and then reuse of certified components. And then for defect removal technologies, you need inspections of various kinds, static analysis, and formal testing using mathematical test case design. Another question, how many of you here have certified test personnel in your company? What? That's a trick question because there are 3 or 4 competing certification groups. I'll settle for any of the competing test certification groups without specifying which one. Okay, see, you know that there's several of them already, but that's probably why you asked the question. But even so, any of them are better than none. How many of you use mathematical methods for designing test cases, like design of experiments? Which, by the way, are you using the technique that Accenture uses? Okay, they use design of inspections as one of the, design of experiments. I said inspection, design of experiments is the basis. Now, defect prevention, JAD, QFD, software reuse, root cause analysis, Six Sigma, model-based requirements design, climbing to at least level 3 on the capability control level, status analysis, and inspections. All are good for defect prevention. In addition to that, life cycle quality measures. Anybody use any of the Japanese techniques like Kaizen, Pokioka, Kanban, or quality circles? Which one are you using? Let me ask you. Are you using Kaizen, Kanban? Kanban? Okay. These work pretty well. That's one of the reasons why Japan has such a high level of quality compared to most other countries. And I hope all of the rest of you using the Japanese stuff are satisfied with it because it looks pretty good to me. Pair programming, which is expensive and not so good. Formal inspections, embedding users with the development team like Agile does, that's pretty good. Scrum, issue-oriented team meetings, that can be effective too. Defect removal. Various kinds of inspections, including test plan and test case inspections. Text static analysis, there are 2 older tools that are useful. One is called the FOG index, one is called the FLESH index. They're readability scores. And they're automated tools that look at the readability of text. And in the state of Florida, insurance companies are required to use these things for insurance policies to be sure people can understand them. but they're very helpful for requirements and for design because they clarify the level of understandability of the documentation. Code static analysis, I've forgotten the name of the tool, but it works with IBM's Rational Unified Process. It's a very powerful static analysis tool, only it works on text instead of on source code, but it finds the same kinds of bugs. And then code inspections, automated testing for unit performance testing, and all forms of manual testing, of which there's actually more than 40 different kinds of testing that can be performed. Some are pretty specialized, some are common. Now, defect removal efficiency. I believe this is the most important single metric in all of quality. DRE, defect removal efficiency, is the ratio of defects found to defects that are present. But how do you know how many defects are present? All you know is the number of defects that are found. Well, you can find published data, like some of my books on assessment and control of software risks have data based on hundreds of companies on how many defects you're likely to find, so you can find it from published sources. So what you want to do is to calculate your defect removal efficiency. If the first operation finds 6 bugs, it's 60% efficient. If the second one finds 2 bugs, it's 50% efficient because you've already found 6, and those together found 8 out of 10 bugs or 80%. So in addition to knowing the overall defect removal efficiency, you want to know the specific defect removal efficiency for each kind of removal. Like everybody does unit testing, okay? Unit testing is only 25 to 35% efficient. Finds about 1 bug out of 3. Most forms of testing are only about 35% efficient, find 1 bug out of 3. That's why testing collectively is not the optimal choice, because you'd have to string together 10 or 12 different kinds of testings to get up into the high 90s for defect removal efficiency if each level of testing is only 35% efficient. That's why you need to plug in some things like inspections that are 85% efficient all by themselves and raise the efficiency of testing afterwards. So you need to get these optimum combinations of things into your own QA organization. Now, here's the same example that I showed before, slightly different flavor. But what I want to show here is the ranges that you're likely to see, because you don't get the same numbers every time you go through it. The lowest efficiency for things like requirements review are 20%, the highest is 50%. The lowest inspection for a code inspection, 35%, the highest is 90%. So what this shows is the combination of cumulative efficiencies based on lowest, average, and highest results. But you can see if you do these 10 things, and even if you only do them in an average fashion, you're going to get up to 98% removal efficiency. But if you leave out some of the things, especially if you leave out some of the high efficiency things like inspections, you're going to be down below 80% in defect removal efficiency. So everybody should plan out a sequence of defect removal activities and operations that will get you up to over 95% in cumulative defect removal efficiency, and it can't be just testing. It also has to include some pre-test inspection, static analysis, and that kind of stuff in order to get to the good numbers at the end. Now, there's another interesting chart that anybody can use. What this shows is a timeline. The bottom axis shows when defects are discovered. And using root cause analysis, the upper line shows where the defects originated. And if you happen to have a discovery pattern that looks like this, where there's acute angles connecting the discovery point of defects from their origin point, you've got severe chronic weakness in your defect removal activities. What you should have is a set of lines that look like this, where none of the defects discovery go into the next phase, where all defects are found in the phase in which they originate. You never want to have something where requirements bugs aren't found until testing or maintenance, because that obviously implies severe weaknesses in your defect removal strategy. So you want to try to use this kind of a graph just to show how things operate. Now, there's a lot of things you can do, and let me show you the results of different combinations. What I have here are 4 different technologies, and these 4 technologies together give me 16 combinations. If you do not use design inspections, if you do not use static analysis or code inspections, if you have no formal QA organization, if you don't do formal testing, if the developers just do their own testing, you're going to be lucky to get 50% defect removal efficiency. Well, what happens if you change one of these things? Okay? If you put in a formal QA group, up to 55%. If you put in formal testing, up to 60%. Put in code inspections, up to 65%. Put in design inspections, up to 68%. Bottom line, one thing is not enough. No things are not enough, and one thing is definitely not enough. Well, let's consider changing 2 things. Okay? You can put in quality assurance and testing. You can put in code inspections and quality assurance. You can put in formal code inspection and formal testing, get up to 80%. Not bad, but not great. Now we've got 3 things. By the time you get to the bottom of the page with the formal design inspection and code inspections, well, no, there's still 2 things. You're up to 90%, which is not bad. These are the 3 things that you can do. By the time you get to the bottom of this page, with formal design inspections, code inspections, and formal testing, but no QA, you could get up to 99%. But why not go all the way to the end? Because here, the lowest you're going to get is 95%. The best you're going to get is 99.99%. And your median value is going to be 99%. The bottom line is that there's no silver bullet. What you get is a silver shotgun shell. You need a lot of silver pellets in order to get improvements like this. There's no single thing you can do, but if you do these 4 things, and you do them well, then you will get up into the high 90s in defect removal efficiency. Now, this is the distribution of defect removal efficiency levels based on a sample of 1,500 projects. 6 of them were over 99%. 104 were between 95 and 99. 263 were between 90 and 95. 559, 85 to 90. 408, 80 to 85, and 161 were below 80% of defect removal efficiency. Now what you want to do is find out exactly where you are today on a chart like this and climb as rapidly as you can up towards at least the 95 to 99% plateau, and ideally up to the 99% plateau. And if you do that, not only will your quality improve, your costs will go down, your schedules will go down, client satisfaction will go down, maintenance costs will almost disappear, and your top executives will suddenly float you high into the company. In fact, even better, the companies that do that, the QA organization will be swept away by other companies for much more money than they're earning where they are now, because once this begins to come out, in fact, that raises another problem. If you go back and revisit companies after 5 or 6 years, you find some of them have dropped back to where they were before. It's because everybody that was part of the process improvement team was hired away, and the replacements didn't know as much, and they didn't keep the techniques that were first installed. So the bottom line, if you do things right, you get all kinds of benefits, and if you don't do things right, then you don't get any of the benefits. So this is some of the topics that need more research. Errors in test plans and test cases. Does any single person in this room measure errors in your test cases? I'll bet the answer is no. Oh, one hand. Do you find many of them? Oh, okay. Well, that's a good thing for you. Errors in web content, such as graphics and sound, that's hard to do. Correlation between security flaws and quality flaws, they got to exist because they're part of the same parcel, but there's no real correlation. Errors in data and creation of a data point metric. You saw how good function points were. The companies own more data than they own software. You can't measure data with function points or anything else. We need a data point metric to look at the volume of errors in data, not just in software itself. Errors in the contents of databases, repositories, causes of bad fix injections. When you fix a bug, what makes you put a fresh bug in there that wasn't there before? And the impact of complexity on quality and defect removal, and the impact of creeping requirements on quality. These are things that need more research than they're actually getting today. Final slide, and then we'll have some questions. No single quality method is adequate by itself. Formal inspections plus static analysis plus models are effective. Inspection, static analysis plus testing are 97% efficient or higher. Defect prevention plus defect removal is best overall. QFD models, inspections, and Six Sigma prevent defects. Higher CMMI levels, TSP, RUP, Agile, and XP are effective. Quality excellence, being good in quality, has over a $15 positive return on investment for every dollar you spent getting there. Better quality is one of the best ROIs of any known technology and software. So the better you get, the more value you're going to achieve from it, both in reduced maintenance costs, larger market shares, and a bunch of other stuff, and high quality benefits, schedules, productivity, users, and all of that stuff at the same time. Well, it's now 9:30. We have 15 minutes if there are any questions. Okay, the question is, what's the difference in numbers between defect detection efficiency, defect removal efficiency? 20 years ago, there was almost no difference. Companies like IBM, if they found 98% of the bugs, they fixed 98% of the bugs. Today, there's a huge difference. A lot of companies are finding 96, 97%, but only fixing 80 to 85% before they deliver because they want to get the software out there early. Bad choice. Not only does it raise technical debt, it makes the companies unhappy, and it's likely to lead to litigation. So ideally, your DDE, defect detection efficiency, and defect removal efficiency should be within 1% of each other. And the only bugs you don't fix are those you find on the actual day of release or maybe a day before. No, it was just the IT cost. By the way, that's a good question. When you deliver software with bugs in it, there are things called consequential damages. These are damages done to the clients themselves, and that was not included here. There's also the cost of litigation, and a typical quality lawsuit is about $3 million for the plaintiff and close to $5 million for the defendant. I didn't show that either. So there's a lot of other costs. This was mostly the direct costs associated with finding and fixing bugs, none of the indirect cost consequential damages. I have data on that, but I didn't have it here. I mean, if you don't measure defect removal efficiency, you don't have your own costs on this basic stuff, you're hardly ready to deal with consequential damages and the more sophisticated kinds. True, but if you measured agile quality, you probably want to go back to the SQA because agile is not that great on quality compared to TSP and RUP. One of the problems with agile is they don't measure enough, and therefore they make claims about things like better quality without having enough substantial data to back it up. If you look at things like TSP and RUP that have things like separate QA organizations, their quality is often better than agile. So telling me that agile is doing something is not saying that agile is doing it wisely or well. They're just doing something, but it turns out not to be the right thing. Well, measure defect removal efficiency, which is easy to do and can be done easily in agile too. And if your agile data is below 90% in DRE consistently, then put in something like a separate QA organization to get it back up above 95%. If you support agile with solid metrics, then you can eliminate some of the agile mistakes that have become endemic. Just telling me that agile does something doesn't tell me anything because agile measures almost nothing. It's almost pitiful in the lack of things that they measure, and it's just not a satisfactory solution. So start measuring the stuff that matters and then improving them. Make agile better, in other words, is what I'm saying, rather than just drifting along with it. All right, this question was about agile and whether agile, which is not using things like formal quality assurance groups, and my observation was that agile should. And they should also measure defect removal efficiency, and then they find out why they should. Well, you can start with Google searches. That's pretty easy to do. There's over 50 static analysis tools, and it's not my job. In fact, it would be probably a conflict of interest to recommend any specific one. But if you start doing Google searches on static analysis tool, you can find both commercial ones that are sold for a fee, or you can find open source ones, and any of them are better than none. So doing no static analysis is definitely a weakness, but which one you use, you can contact the user groups, you can get information from Google, but I can't, in consciousness, recommend one because half a dozen of them are clients, and I don't want to talk about one without insulting the others. What? There's no real cost to get started. You just do a Google search and then start ordering. If you want to start with the open source ones or the ones that don't cost anything, that certainly has a low startup cost. Inspections don't cost very much either. You can buy textbooks that explain how to do it, or you can bring in instructors to teach you how to do it, but it's only a couple of day class. So that's not a big deal either. The total is today around 20,000 projects divided by 24 countries. Most of the data comes from the United States, but I've worked in many other countries and I have a lot of data from Japan, from Germany, from Scandinavia. Why does that even matter? 20,000 projects from hundreds of large companies is the source of my data, but I have non-disclosure agreements. I can't go giving you the specific names of my clients. Nobody can. You couldn't expect somebody to give you the specific names of clients. The fact that it's Fortune 500 companies in 24 countries should be enough for today. In fact, that it's 20,000 projects should be enough. Okay. Thank you very much. Thank you.